A hyperbola is the set of all points in a plane, the difference of which, the distance from two fixed points called foci, is constant. The first thing I would like to draw your attention to is this word difference. The only change between the definition of an ellipse and the definition of a hyperbola is this word. In the definition for an ellipse, this word is the sum of which, and here for the hyperbola, it's the difference of which. It's a very subtle change, and it's the only thing that differs a hyperbola from an ellipse. All right, here I have drawn some rough sketches of what our hyperbolas can look like. So our hyperbolas, first of all, have two branches, and the branches can open to the left and to the right, or the branches can open up and downward, up and down. Okay, and I'll show you how you can, tell which case you're in for each problem. You have a center, you have a pair of vertices, and you have a pair of foci, just like you did for an ellipse. Okay, so what I want you to notice is the definition for a hyperbola. Let me call out a point on one of these branches. So I called out a random point that's on there we go, that's on the hyperbolic curve here. So this point here is on the hyperbola because this distance to one focus and then minus the other distance, the difference of these two different distances, the difference between these two distances is constant for every single point on the hyperbola. So if I take another point on the hyperbola, like say over here, let's just say, then the distance that this point is to this focus, and then minus this distance here to the other focus, will be the same as this, the difference of the distances for this point here. This is the definition for a hyperbola. Same thing is true for a hyperbola opening upward and downward. Okay? All right, now the standard form for a hyperbola, the standard form for the equation of a hyperbola looks awfully familiar, and this is what it is. The standard form will be x squared over a squared, and then you have a y squared over b squared. That already looks familiar, doesn't it? Is equal to 1. This looks like the equation for an ellipse. Instead, you're going to have a minus here. That minus, that difference, is coming from that word difference in the definition for a hyperbola. Notice the only difference between the equation for a hyperbola and an ellipse has a plus sign right here. Now remember, this is the standard form for a hyperbola that's centered at the origin. Furthermore, this is the equation for a hyperbola centered at the origin that is opening sideways like this. So this, like this one right here, right? So this equation, move this over a little bit, this equation that I've written is the standard form for equation of a hyperbola that's opening left and right. For the standard form for an equation that's opening up and down, watch this, is the following: y squared over a squared minus x squared over b squared is equal to 1. Do you notice the difference? The only difference is that the y term comes first. If the y term comes first in your equation, then this is the equation for a hyperbola opening up and down. It's that simple, ladies and gentlemen. What term comes first in your equation? X comes first? Okay, then that means you have a hyperbola opening left and right. At y comes first? Okay, your hyperbola opens up and down. I should probably be a little more careful. When I say it comes first, I mean x is positive, so it's x and then minus y. Okay, it's opening sideways like this. If it's y minus x, right, it's opening up and down. So it's that simple. Now, again, these equations are the equations for a hyperbola that's centered at the origin. If we shift these hyperbolas in the plane, then remember our conversation on transformations. X minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. This represents a hyperbola that has been shifted away from the origin. So the origin is no longer the, I'm just fixing that. The origin is no longer the center, okay? H comma k is a center. Let me put a line here separating these. And then this one over here would be y minus k quantity squared over a squared minus x minus h quantity squared over b squared is equal to 1. Okay? So even if the hyperbola is not centered at the origin, these are your equations here. Your center is h comma k. H comma k. Be careful. H is always with x and k is always with y. All right? Now, this is what I would like to do. I want to show you, I'm going to scroll back down, okay? So I want to show you the picture here before we look at an example. You see these pictures? I think I want to write this down for you. A, not a squared, but A gives you the distance from the center to the vertex. And that is the same information that you wrote down for the ellipse as well. A is the distance from the center to the vertex. C is the distance from the center to the focus. Same thing over here, everybody. For this hyperbola opening up and down, the distance from the center to the vertex is A. The center to the vertex is A. C is going to tell you the distance from the center to the focus. So let me tell you let me tell you how to find C, okay? This is how you find C. C squared is equal to A squared plus B squared. All right? So this, I don't know if you recall, but when you had an ellipse and you were looking for C, this sign right here was minus. And now when you have a hyperbola, this sign is plus. I don't know if this helps you or not, but you know this sign right here, the standard form for a hyperbola, that's a minus. So when you go find C, that's going to be plus, opposite sign. The same is true for an ellipse. So whenever you need to find your foci, then you need to know what C is equal to, and this is the equation that will always give you C. Okay? Now, what I have not told you yet is what B is used for. Okay? What does B represent? It represents a distance, and I'll show you that actually in a problem. Okay? Okay, guys, graph this hyperbola. X squared over 4 minus y squared over 9 is equal to 1. Okay, if I didn't tell you this was a hyperbola, this was the equation for a hyperbola, you should know. How? Well, first of all, this is not a plus sign. If this were a sum, then this is the equation for an ellipse. Okay? If these denominators were exactly the same, 4 and 4 and 9 and 9 or 1 and 1, and this were a sum, then that would be for a circle, okay? But because this is a difference, it's a hyperbola. Now, which term comes first, x or y? You can see x does. So you already know that this hyperbola opens to the left and to the right. Now, you can see that there is no shifting or no translation happening here. So my center is 0, 0, all right? Here, to drive home that point, I can rewrite this, if I wanted to, as x minus 0 quantity squared over 2 squared minus y minus 0 quantity squared over 3 squared, which is 1. Cool? So this is what we know so far. The hyperbola opens left and right because x term comes first, and the center is 0, 0. A is 2, and B is 3. All right? All right, watch this. I'm going to show you how to graph this hyperbola. All right, first things first, let's graph, or plot rather, our center. So our center is 0, 0. Now, if I move to the left and to the right 2 units, I'll hit my vertices. Remember, A gives you the distance from the center to the vertices. So 2 units to the left and 2 units to the right. Okay, so these are my vertices. Okay, now watch what I do with the distance of b equal to 3. Watch what I do here. What I'm going to do is from my center, I'm going to move up 3 units and I'm going to move down 3 units. Okay? Now, what you're going to see me do is create a rectangle with these 4 points here. These vertices and this point and this point. All right? What I'm going to do is I'm going to create a rectangle. Yes, a rectangle, and it's going to go through my 4 points here, the 2 red one, my vertices and those 2 blue points. And this rectangle is going to help me draw my asymptotes. The hyperbolas that you're going to be graphing are going to be approaching asymptotes. You're used to asymptotes, right? But these asymptotes are going to be diagonal asymptotes. Let me show you how you're going to find them, all right? So create your rectangle, something like this, through these 4 points that you just finished finding, right? You see me do that? And then what I want you to do is extend the diagonals of your rectangle. So this is the diagonal of your rectangle. That's a diagonal. I want you to extend it like that. Here's the other diagonal, right, of the rectangle. Extend it like that. Okay? And what your hyperbola is going to do, each of these branches, you already found the vertices. What they're going to do is they're going to get infinitely close to these asymptotes, like that. Okay? And so what you see in red here, what you see in red are your hyperbolas, are the branches for your hyperbolas. Okay? So I needed some guidance on how wide opening these hyperbolas are or how narrow opening these hyperbolas are. And so these asymptotes here, these are asymptotes, they help me determine what these hyperbolic branches look like, how wide opening, okay? So that's the purpose of the asymptotes. The graph of the hyperbolas, they're not allowed to touch these asymptotes, but they get infinitely close to them. Okay, so let me label a few things for you. Okay, so I have labeled our asymptotes here. You got a pair of asymptotes every single time. And we found our vertices through which our branches pass. And we've graphed the hyperbola. I guess we're done, but just to show you, for the sake of showing you, and for teaching, I want to show you how to find your foci. Let me move this up a little bit, okay? Now, your foci is found by using this equation. C squared is equal to A squared plus B squared, okay? So then it's equal to, A squared is 4, right? And then B squared is 9. So it's equal to 13. That's what C squared is equal to. So then C is equal to the square root of 13, right? After taking the square root of both sides. So what I would like to do is I would actually like to plot these two foci. It's going to be about right there. There's one focus, and the other focus is over here. What I would like to highlight for you is that your foci are always within, kind of trapped within the hyperbola branches, right? Hyperbolic branches. So it's always trapped inside of the branch right here. So it's inside the branch. So in other words, it would have been impossible for the foci to be over here between the center and the vertex. No. It's going to be to the right of it and to the left of it, or rather trapped between the branches, okay? Okay, guys, let's look at our next example. Again, if I just said graph, if the instructions just said graph, you should know this is a hyperbola without anyone telling you because of that difference right there, okay? All right, now which term comes first? The y term comes first. It's y and then minus x, right? So this hyperbola will be opening up and down. Don't forget that h is always with x and k is always with y. So the center is going to be positive 1, negative 2. Don't get that turned around. Positive 1, negative 2. This is h, comma, k. So this is what we know, you guys. The hyperbola opens up and down. Again, we know that because y comes first. The center is, be careful, +1, -2. That's h, comma k. A is 5 because 5 squared gives you 25. And b is 4 because 4 squared gives you 16. If you want to find your foci, which we do, use this relationship that c squared is equal to a squared plus b squared. So that's 25 plus 16, which is 41. That's what c squared is equal to. That must mean c is equal to the square root of 41. Okay? So let's see if we can get our graph started, okay? Okay, guys, this is everything we know up top, and I'm going to get our graph started now. Okay, you guys, I have my axes scaled. I think this will be good enough, in spite of how sloppy it looks. It'll be good enough to show you what's happening. My center is 1, -2. I'll plot that first. So 1, -2 is about right there. There's my center. And the distance a equal to 5, this distance right here, since this hyperbola is opening up and down, this is the distance that if I move 5 units up and down from my center, I will reach my vertices. So let's do that. So this is the point 1, -2 right here, and I want to go up 5 units. If I go up 5 units from this point, I end up at, let's see, 1, 2, 3, 4, 5. I ended up at 1, +3. That's a vertex. 1, +3. Okay? And then another, I can plot that if you like, or show that. If I go down 5 units from my center, I'll end up at 1, -7, about right here. Okay, that's the other vertex. 1, -7, about right there. That's the other vertex. Now, I want to move to the left and to the right 4 units from my center because that's what B is. B is 4. So from my center, I'm going to move 4 units to the right, 4 units to the left, and those points will help me draw that rectangle that will help me draw, my asymptotes. So here we go. Let's go 4 units, everybody, to the right of my center. So when I move 4 units this way, I end up at 5, -2. So about right there, okay? And then when I go 5 units, not 5 units, excuse me, 4 units to the left, I end up at -3, -2. About right there, okay? And like I showed you in the previous example, I am going to endeavor to draw a rectangle through these 4 plotted points, the 2 vertices, and these 2 blue points here. And the extended diagonals of the rectangle will be the asymptotes for my graph. So let's see if I can do this here. So let's go through this vertex here, through this point, up to the other vertex here, through this blue point there, and through the other vertex there. Cool? And now we want to extend the diagonals of this rectangle. Let me grab a different color for us here. So maybe just white. So I'm going to draw right through the center, draw the extended diagonals through the center here, there. Cool. Now these, what we just drew, are the asymptotes that each of your branches will get infinitely close to. So now let me go to each of my vertices and get infinitely close to that asymptote, and then down here, infinitely close to that line and to that line there. Okay. Okay, guys, I hope this is helpful. I labeled everything here. I labeled my center, I labeled my vertices with the coordinates, and I labeled these points here that my rectangle goes through. And what I also want to label are your foci. Now, your foci are the square root of 41 units away from your center, up and down, right? So one of the foci is going to be in here in this branch, and the other one's going to be in here inside of this branch. Without using my calculator, I know that the square root of 41 is more than the square root of 36, which is 6. And I know it's less than the square root of 49, which is 7. So I know the square root of 41 is between 6 and 7 units. Okay, between 6 or 7 units. So when I move from my center, when I move up the square root of 41 units, I'm going to end up more than 6 units up, right? Which would be between 4 and 5 units on the y-axis. So about right there, okay? So my first focus is going to be about right there, okay? Let me give you coordinates for that. So here are the exact coordinates for that focus. 1, comma, -2 plus root 41, right? So I basically added root 41 to that coordinate. Now I'm going to start at my center and go down the square root of 41 units. That will drop me off a little bit below -8. Okay, a little bit below -8. So let me plot that for us. Because remember, the square root of 41 is a little bit more than 6 units. So maybe about right here, you guys. And let me give you coordinates for that. So I have these coordinates for this focus here. So it's 1, and then -2 minus, or -2 minus the square root of 41. Okay, so I have everything here on the screen. I got my center, I got my vertices, and I have my foci. I even have my asymptotes right here. Cool? Here's our next example, guys. Graph 2x squared minus y squared plus 4y minus 12. Now, this is very similar to the examples that we saw for the ellipse and for the circle, where we have to complete the square in x and in y in order to rewrite this equation in standard form. So the first thing you'll see me do is to group my terms together. So we have 2x squared. That's the only x term, by the way. And then we got minus. Now watch what I do here. I am going to do y squared minus 4y. I'm going to move that 12 over to the other side. It becomes positive. I want you to notice my sign change here. You see how this is positive 4y? When I group both of these terms, I pulled this negative out of both of these. I factored out the negative out of both of these right here. I mean, just imagine this negative being distributed back inside. What would you get? Negative y squared, bingo. And then you would get a negative times a negative. That's a positive 4y, bingo, right? So the reason why I factored out a negative from both of these terms is because in order to complete the square, the leading coefficient has to be positive 1, and now it is. Okay, so let's complete the square in y. I know I said up here, complete the square in x and y. Generally speaking, you have to do that. But because you only have this x term by itself, we will not be completing the square in x, okay? If there was another x term, like there's 2 y terms here, then I would be completing the square in x as well. Okay, so then remember, this is how we complete the square. We take the coefficient of the first degree term for y. I'm completing the square in y. So take -4 and take half of that, which is -2, of course. And then take -2 and you square it, and it becomes positive 4. So I'm going to squeeze in a positive 4 right there in that y group, if you will. So then I end up with 2x squared. Let me go back here. Write in one color here. Okay, so then I'm going to end up with 2x squared minus y squared minus 4y plus 4 is equal to 12. Now you're going to have to be very careful here. Remember, whatever you add to the left-hand side of the equation, you have to add the same amount to the right. Now, it's very tempting for me to say, oh, I added 4 to the left. Let me add 4 to the right. But that wouldn't be correct because there's a negative out front. So really, you've added -1 times 4. You've added -4 to the left. So you're going to have to add a -4 to the right. When you say you're adding negative 4, that's the same thing as saying you're subtracting 4. So you got to be very careful about that, okay? So then this becomes 2x squared minus, and then this is y minus 2 quantity squared is equal to positive 8. Cool. Now, this equation is not in standard form until this constant term over here is 1, right? So what do we divide both sides in order to get this number to be a 1? Divide it by itself, divided by 8. So if you divide this by 8, 8 divided by 8, of course, is 1. But you're going to have to divide everybody by 8, right? On both sides. So then you get x squared over 4 here, because 2 divides into 8 4 times, right? Minus, and then you got y minus 2 quantity squared over 8 is equal to 1. Now this is the standard form for the hyperbola that we are to graph. Okay, let me just box this for us and then maybe move up the screen. Okay, so we completed the square. Now we can notice a few things. Well, a lot of things actually. We notice that the x term comes first, right? So that tells me that this hyperbola is going to be opening to the left and to the right. I can see my a value is 2 because 2 squared gives me 4. And my b value is the square root of 8, right? Because the square root of 8 squared gives me 8. Okay, I can see that my center is 0, comma, positive 2. Okay, so this is what we know so far. Now, of course, you and I need to find c, right? Because that's going to give us our foci. So c squared is equal to a squared plus b squared. So c squared is equal to 4 plus 8. This is c squared. So c squared is equal to 12, right? So that means c is equal to the square root of 12, okay? That can be simplified if you want as 2 root 3, okay? 2 root 3, if you want to simplify the square root of 12. Maybe I should show you how I simplified that. So the square root of 12 can be rewritten as the square root of 4 times the square root of 3. And the square root of 4 is just 2, and then the square root of 3 is irrational, okay? All right, so that's what c is, or you can just say c is the square root of 12. Okay, everybody, I'm going to plot the center first, 0, 2. Now, remember this hyperbola is opening to the left and to the right. And so what I want to do is I want to move to the left and to the right a number of units, which is 2 units. So 2 units to the left, 2 units to the right, and that will drop me off at my vertices. So 2 units to the left puts me at -2, +2, that's one vertex. 2 units to the right puts me at 2, 2, that's the other vertex. All right, cool. And now what I'm going to do is I'm going to move up and down from my center b number of units. Okay, square root of 8, everybody. Square root of 8 is a little bit less than 3. How do I know that? Well, the square root of 9 would be exactly 3. The square root of 8 is slightly less than the square root of 9. So we're moving almost 3 units up and 3 units down. Okay, so 3 units up would put me, I'm going to go 3 units up and then I'll just move down just a little bit. So 1, 2, 3 units up, and then so it's a little bit less than 3 units up. So it's a little bit underneath the 5 on the y-axis, okay? So about right there, everybody. And then 3 units down, 1, 2, 3. So it's about right here, okay? Not quite 3 units. Cool. Now, what I'll do is I'll draw that rectangle. Okay, guys, I have my rectangle drawn, and we know that the asymptotes for the graph will be the extended diagonals of this rectangle. So go right through your center, extend the diagonals. These asymptotes should be drawn with a dashed line. It's a little easier for me to do a solid line, but it's okay. All right, here we go. So then this vertex here, which is 2, 2, will get infinitely close to these asymptotes. Each of them will get infinitely close to the asymptotes. So what you see in red are the branches of the hyperbola. The only thing that's, I guess, a little, that's missing are the foci. Now remember, the foci are found by finding c, which we found already, square root of 12. The square root of 12 is larger than the square root of 9, so it's more than 3, but it's less than the square root of 16, which is less than 4. So it's between 3 or 4 units, okay? You can get an approximation by plugging it into your calculator. What I'll do is I'll move from my center to the right square root of 12 units. So between 3 or 4 units to the right, okay? So then, if you moved 3 units, it would put you at 3, 2. It would put you right here. If you moved 4 units, that would put you at 4, 2. So we're in between there somewhere, all right? Because we're graphing by hand, we want to, this is just a sketch. And then the same thing on the left-hand side. Okay, so each one of those are your foci. I'll actually label those coordinates now. Okay, so the coordinates for this focus is a square root of 12, comma 2, and then the negative square root of 12, comma 2. All right, you guys, that's everything. Good job. Look at this example. They're actually not asking us to graph it. They're just asking us to find the center and the direction the following hyperbola opens by converting this equation to standard form. All right, so in order to convert it to standard form, we have to complete the square in x, complete the square in y, just like we did a little while ago. So you're going to see me gathering my x terms together. We've done this now a few times with our circles, with our ellipses. We've even done it with the hyperbola, so we're doing it now again. I'm moving the 11 over. And then again, I want to highlight here, just want to be careful with my signs. When I collected my y terms together, I factored out the negative right away. So that changed the positive 18 to negative 18. Okay, before you complete the square in x or y, this leading coefficient, each of them has to be factored out so that the leading coefficient is 1. So you're going to see me factor out the 4. You're going to see me factor out the 3. Now I can complete the square, okay? So I'm going to take half of the coefficient of the first degree term for each of these variables. So I'm going to take the number 2, take half of that, which of course is 1. I square that, which is 1. For the y variables, I'll take half of negative 6, which is negative 3. And then I'll square negative 3, which is 9. So here we go. I'm going to put a 1 right here in that group. And for this group, we'll be adding a 9. Now, you're going to have to be very careful here to add the same numbers to the right-hand side. Now, we've got to be careful. I know we wrote a 4. Oh, excuse me, I got ahead of myself. I know we wrote a 1 here, but in essence, we actually added 4 because 4 times 1 is 4. So we really added 4 to the left-hand side, so you need to add 4 to the right as well. Furthermore, I know you wrote 9 here, but you really added negative 3 times 9. You've really added negative 27. If you added negative 27 to the left, you have to add negative 27 to the right as well. Adding negative 27 is the same thing as subtracting 27. All right, cool. Now we can factor, right? So we have 4 times x plus 1 quantity squared. We're almost there. Minus 3 times y minus 3 quantity squared is equal to, what is this, 15? 11 plus 4 is 15, and then 15 minus 27 is negative 12. Cool. Now, in order to have this equation in standard form, this negative 12 needs to be a positive 1. What are we going to divide both sides by? By negative 12, that's right. Negative 12. Let me move the screen up. Now this is going to give us a negative. The first term is going to be negative. So you're going to have x plus 1 quantity squared. Now that 4 in the numerator, the 4 in the numerator divides into 12 3 times. That negative is still there. I just put it out in the front. So the denominator is 3. And then notice that this second term is going to be positive because you got two negatives. And then you got y minus 3 quantity squared. And look at that 3, it goes into the 12 4 times, is equal to positive 1. Now, because this first term is negative and this second term is positive, I'm going to rewrite this as y minus 3 quantity squared over 4, and then minus x plus 1 quantity squared over 3 is equal to 1. There. Now you can see this is standard form. This is standard form. And which term is coming first? The y term is coming first. Ooh, it would have been dangerous to say x is coming first. This is not in standard form yet because it has to be the first term minus the second, right? And so now it is. So the y term is coming first. Because the y term is coming first, this hyperbola is opening up and down. Now be careful when you identify the center. It's h comma k, and h is always with x, and k is always with y. So it's -1, +3. So there we have it. The hyperbola opens up and down, and the center is -1, +3. Cool deal. They did not ask us to graph it, so don't worry about it. All right, everybody, this is going to be our last example. Find the equation in standard form of the hyperbola with vertices at 0, +6, and 0, -6, and foci at 0, 10, and 0, -10. Okay, just like the other sections, I think it's a good idea. It would be really smart of us if we were to show a little picture of what's going on. So, and now it's going to be a short little sketch, okay, everybody? So I am not being super detailed, okay? This is what they gave you. Your vertices are at 0, 6 and 0, -6. And your foci are at 0, 10 and 0, -10. Focus, focus. The yellow ones are your vertices. So this parabola, I hope you can see that this parabola is going to have to open upward and downward. Okay? Now, do you see what your center is going to be now that you've graphed a little bit? Do you see that the center is going to be right at the origin? Cool. So let me move this down a little bit, okay? Okay, because this hyperbola is going to open up and down, we know the y term has to come first, right? So it's going to have to be of this form. Like this. Cool. In order to finish this off, we need to know what the center is. We do. It's 0, 0. And don't forget that A represents the distance from the center to your vertices. So A is, what, 6 units? I can highlight that for us if you want. This is A, which is 6 units, right? That's what A is. So then let's see what we have here. We have y minus 0 quantity squared over A, which is 6 units, so 6 squared, minus x minus 0 quantity squared over B squared is equal to 1. So then the only thing that's missing is B, okay? Do you know what C is? C was given to you. C is the distance from your center to your foci, but the distance from your center to your foci is 10 units, isn't it? Look at the picture. The distance from the center, here I can show you, remind you. Oops. The distance from this center to this focus is 10 units. So C must be 10, right? This distance here, right there, C must be 10. So then they gave us C. They gave us, really they gave us A as well. So what's missing is B in order to finish this off. So let's find B. Do you remember the relationship for a hyperbola? It's C squared is equal to A squared plus B squared. So plugging everything in, we would have 10 squared. I need more room here. So let's see, 10 squared is equal to A squared, which is 6 squared, right? Plus B squared. And let's just solve this for let's solve this for b squared. Okay, so then subtract 36 from both sides, and that'll be b squared. So then b squared is equal to 64. Yeah, that's right, 64. Cool, that was the last missing piece for standard form. So then standard form is going to be, remember you had y minus 0 quantity squared? You can just write that as y squared over a squared, which was 36, because a is 6, minus x minus 0 quantity squared can just be rewritten as just x squared, over b squared, which is 64, and this is equal to 1. Cool deal. You and I did it. I think what's key here is that you and I sketch a little diagram of what's going on, and then we can fill in the missing pieces.